Hello everyone, this is Teacher Harold, your junior high school math teacher. And in this video, let us now have the fifth lesson in Mathematics 9, which is about simplifying expressions using laws of radicals. After you watch this video, you should be able to use or apply the laws of radicals to simplify related expressions. In this module, you would be able to study the laws that can be used to express radicals in simplest form. The topic from this material is important in order to prepare you to study the principles of simplifying radical expressions, leading to the skills of solving related word problems. For our next slide presentation, in order for us to simplify related radical expressions, we must consider the following laws of radicals. So from this presentation, we have 5 different laws of radicals. Now, these laws are used to express radicals in simplest form. So for any real numbers represented by x and y, and m and n represented by for any real numbers x and y which represents real numbers, and m and n representing positive integers, we have the following laws. For number 1, we have the nth root of xy is equal to the nth root of x multiplied by the nth root of y. So again, you will verbally read this as the nth root of the product of xy, which is equal to the product of nth root of x times nth root of y of the nth roots. Now for number 2, the nth root of a quotient of the nth root of the quantity x over y is the quotient of the nth root of x over the nth root of y. And for the third law, you will notice that the left side is a nested radical. The mth root of the nth root of x is equal to the mnth root of xy. So basically, the two different indices is to be multiplied, whose product would be the index of the answer. So that is the mnth root of the same radicand represented by x. So for this third law, again, you read this as the mth root of the nth root of x, which is equivalent to the m times nth root of that integer x. And for number 4, the nth root of x to the n is equal to x. Now, there is a certain condition for this particular law. If x is a real number and n, or the index represented by small letter n, is an odd. Okay, so it's just the answer is simply x. Now, what about number 5? You will notice that the left side of the formula for the fourth and fifth law are the same. Okay, but when it comes to their answers, they're different. Okay, so the answer for number 4 is x, provided that x is a real number and n, which is an index, is an odd. But when it comes to number 5, we have the nth root of x to the n is equal to the absolute value of x. Now, of course, there is a condition, and that is if x is also a real number but the index n is an even number. Okay, now for us to fully understand uh, the the difference between law number 4 and law number 5, we will go to some some illustrative examples for these related laws of radicals. Now let us go back to the first law and let us consider under this law some illustrative examples. Like this one, the square root of 9, the square root of the product of 9 and 4 can be simplified like this. It's equal to the square root of 9 times the square root of 4. And each factor has a perfect square radicand, so we could easily evaluate each of these factors. And this will become what? 3 for square root of 9 multiplied by 2, which is the square root of 4. And the product is 6, which is our answer. Okay? Next. For law of exponent number 2, let us have this example. So cube root of the quotient of 64 over 8, which can be expressed as the cube root of 64 over the cube root of 8. And 64 and 8 are both perfect squares. So if we're going to evaluate the numerator and the denominator, for the numerator it's 4 over the denominator, which is 2. And we know that 4 divided by 2 is equal to 2. And this is your answer. Okay? Now we go to number 3, the third law of exponent number 3. The mth root of the nth root of x is equal to the mnth root of x. Let us have an example. Say 6th root of 64. Now 6th root of 64 can be transformed into a nested radical. Now this given radical is the same as the square root of the cube root of 64, because if we're going to multiply the inner index 3 to the outer index 2, which is not written in radical form, the product would be 6. Now evaluating the inner radical, which is cube root of 64, that will give you 4, and what will remain is the outer radical sign, which is square root of this particular radical, which is 4. So square root of 4 will give us 2. Okay, so we now proceed to the next law, which is the fourth law. The nth root of x to the n is equal to x. For our example, okay, again, we go back to the condition under this law. Now, this particular law can be considered if x is a real number and the index n is an odd number. So, let's just say for letter A example under number 4, the cube root of quantity negative 4 cube, it will give us, of course, you evaluate the radicand, quantity negative 4 cube, that will give us negative 64. And for the cube root of negative 64, it will give us negative 4. Okay. Now for letter B, the cube root of 7 cube, that will give us cube root of 343, which is equal to 7. Next, letter C, the fifth root of the quantity negative 11 to the fifth, that will give us negative 11. And for the last example under number 4, the fifth root of positive 11 to the fifth, that will give us 11. Okay? So basically, we are just following the fourth law, and we apply this law to each of these 4 examples. Okay? So indeed, the condition is that the radicand x is a real number and the index n is an odd. So each of these examples has an odd index. Okay. Now we go to the fifth one. The nth root of x to the n is equal to the absolute value of x. Now why is it that the answer has an absolute value? Because from the condition, your x is a real number, but when it comes to the index, the value is an even number. So, let us have some examples. The fourth root of 2 to the fourth, that is fourth root of 16. You evaluate 2 to the fourth, it's 16. Then you get the fourth root of 16, that will give us the absolute value 2. Now, what is the absolute value of 2? That is equal to 2. Okay. Next, for letter B, how about the fourth root of negative 3 to the fourth? It's fourth root of positive 81, which is equal to 3. The absolute value of 3, or that is equal to 3. It's actually absolute value of negative 3, which is 3. Next, about letter C. Sixth root of quantity negative 7 to the sixth, that is equal to the absolute value of negative 7, or that is equal to 7. And finally, letter D, the eighth root of 11 to the eighth, that is equal to the absolute value of 11, which is, in turn, that is equal to 11. Okay? Now let us go to the next slide. And this time, applying those previous laws from the previous slides, let us now consider this set of illustrative examples. We have number 1, simplify each radical expression. The square root of 32. Now you will notice that the radicand here is not a perfect square, but we could still simplify this by extracting the largest perfect square factor from 32. And that is what? 16. And what is that second factor when multiplied by 16 will give us 32. So basically what we're going to do here is we simply divide 32 by 16 in order to get the second factor. And we know that is equal to 2. So at this point, we have 2 radicand factors. One is a perfect square, which is 16, and the other one is 2. Then, applying the law of the first law of radical, this can be expressed as square root of 16 times the square root of 2. We know that square root of 16 is equal to 4. So, followed by square root of 2. So, the final answer is 4 square root of 2. For our next example, letter B, how about this one? The cube root of 24. Now, since the index is 3, what we're going to do here is we extract a perfect cube factor from 24. And that is, as we all know, is 8. So, 8. And where do we multiply 8? in what number are we going to multiply 8 in order to get the product of 24? So basically, 24 divided by 8 will give us the second radicand factor, which is 3. And applying the first law of radical, this can be expressed as the cube root of 8 times the cube root of 3. And we know that 8 is a perfect cube, so we could easily get its cube root, and we know that is equal to 2 followed by cube root of 3. And this is your answer. Next, letter C. How about the the square root of x to the fifth? Okay, so this is the solution. We're going to extract a perfect square factor from x to the fifth. So basically, we think of a number lower than 5 which is divisible by 2. And we know that is equal to 4. Why? Because this can be expressed as x raised to the 4th, okay? And what number are we going to multiply x to the 4th in order to get a product of x to the 5th? So basically, we divide this given radicand to this one. X to the 5th divided by x to the 4th, that is x raised to 5 minus 4 is 1. So x to the first, or simply x. Then, just like in letter A and letter B, each factor has its own radical sign. So we have, okay. So we have the square root of 4. Actually, it will go first to this process, which I have not, I did not include, no? First, it should be square root of x to the 4th times the square root of x. And square root of x to the 4th is actually x squared, then followed by square root of x. And this is the answer. Okay? Next. Letter D. How about the square root of the cube root of 2y? Now, we know that the outer radical has an index of 2 and the inner radical has an index of 3. So, applying the nested radical rule, we simply get the product of the indices. So, 2 times 3, it will give us 6. So, this is the 6th root of 2y. So, 2 multiplied by 3, it's 6th root of 2y. And this is your answer. Okay, next. Letter E. About the square root of 12 over the square root of 3. Now, the given expression can be written with only one radical sign since they have the same index, which are both 2. So that can be expressed also as the square root of the quantity 12 divided by 3. And we know 12 divided by 3 is equal to 4. So this will become square root of 4, and in turn it becomes 2. Okay, next. Letter F. How about this one? Cube root of the quantity 2a to the 5th b to the 6th over the cube root of the quantity 16c to the 9th. Okay. Now for our solution, rewriting the given, since both numerator and denominator have the same index, the two radicand can be written as 1. Okay. So this is what happened first. Okay, so we extract from this given radicand, we extract the perfect cube factor. So a to the 5th, from a to the 5th, we extract a cube. And from b to the 6th, since exponent 6 is a perfect cube, Why do we know that b to the 6 is a perfect cube? Because its exponent is divisible by the index 3. Okay? So we extract a cube b to the 6. Yun, dito. And so we did not include what? 2 and uh, the one that is left from a to the 5th, which is a squared. Okay? And this is actually, okay, cube root of 2 followed by cube root of a squared all over. Okay, we do the same thing. We extract the perfect cube factor from 16c to the 9. Okay, now 16 has a perfect cube factor, and we extract that factor from this number, which is 8, and c to the 9. So what is left from this radicand is what? 2. Okay, so multiplied by cube root of 2. And at this point, you will notice that cube root of 2 is common, so we could cancel them out from the numerator and denominator. And what will remain here is this one. So we can now evaluate the cube root of the quantity a cube b to the 6. And that is what? A b squared followed by cube root of a squared all over, okay, cube root of 8c to the 9th. That will give you 2c cubed. And this is your answer. Next. For number 2, how about this one? Express in simplest radical form the fourth root of 4. Now for our solution, fourth root of 4 can be expressed as what? Fourth root of 2 squared. So the radicand 4 is replaced by 2 squared. And what will happen here is, okay, there is a common factor from the index and the exponent of the radicand 2, and that is the greatest common factor, which is 2. So that from if we if we cancel the greatest common factor, what will remain from 4 as an index is 2, and 2 from this exponent will become 1. So basically, the simplest radical form would be what? Square root of 2. Next, letter B. How about the 6th root of 125? Now, 125, okay, can be written as 5 cubed. And we cancel the common factor of between 6 and 3. The common factor of 6 and 3, and we know that is 3. So that 6 becomes 2 and 3 becomes 1. So basically, letter B can be expressed in its simplest radical form as square root of 5. Okay. Next. Or, if we consider an alternate solution, okay, we could also use the nested radical form. The 6th root can be expressed as the square root of the cube root of 125. We know that cube root of 125 is 5. Therefore, the final answer is the same, square root of 5. Okay. Next, letter C. How about the 15th root of 243? Now, for our solution, 243 can be expressed as 3 to the 5th, like this. And we cancel the greatest common factor from 15 and 5. And we know that is 5. Okay? Or, we could write this radical form to an expression with radical exponent. So this can also be written as 3 raised to 5 over 15th. And we cancel the greatest common factor of 5 and 15. And that this will become 1/3. From 5 over 15, it becomes 1/3. 3 to the 1/3, and then we restore it back to its radical form. So 3 to the 1/3 is actually cube root of 3. Okay, next. Letter D, how about this one? The fifth root of the cube root of quantity a plus b to the fourth. This is actually the same as the 15th root of the quantity a plus b to the fourth. And this is your answer. Next. Letter E. How about this one? This one. M to the 1/2, M to the 2/3. Now basically, we have expressions with rational exponents, but you will notice that we have two fractional exponents having different denominators. So what we're going to do here is make the two fractions similar by making their denominators the same. So basically, what we're going to apply here is the LCD. And particularly, what is the LCD of denominators 2 and 3? That is 6. Now, since we have the LCD, we will have new numerators for the first fraction and the second fraction. For the first fraction, it becomes 3 over 6, while on the second fraction, it becomes 4 over 6. Okay? So basically, how did we get those numerators? It's actually like this. 6 divided by 2 is 3 times 1, 3. Then for the second fraction, 6 divided by 3, that is 2. 2 times 2 is 4. Okay? Next. Then we apply, we rewrite each factor in radical form. So that is 6th root of m cubed times the 6th root of m to the 4th. And applying the first law of radicals, two radical factors with the same index can be written in an expression with only one radical sign, with the same index 6. So this is the same as the 6th root of the product of m cubed and the m to the 4th. Yan. Okay? This is your answer. Next, letter F. How about this one? 2x times the square root of 98x to the 4th, y to the 9th, z to the 6th. Now for our solution, we rewrite the given, and for our first step of this solution, we basically extract the perfect square factor from this radicand. And the perfect square factor is actually 49x to the 4th, y to the 8th, z to the 6th. Why did we consider this particular factor, x to the 4th? Simply because its exponent 4 is divisible by the index 2. But when it comes to y to the 9th, 9 as we all know cannot exactly be divided by 2. So we only consider the exponent of y, which is lower than 9, and at the same time an even number or divisible by 2, and that is 8. So the perfect square factor that we could extract from this particular factor is y to the 8. And z to the 6 is an even number. So this whole factor is the perfect square. Yun. Then of course, since we extract the perfect square factor from this radicand, now there is a factor that is left from this radicand, and that is what? 2 and y. So basically, after we write this perfect square radicand factor, it is still followed by the square root of 2y. And then, we get the square root of this radicand. So this will become what? Of course, it follows by 2x. We just copy this coefficient. then followed by 7x squared, y to the fourth, z cubed, times the square root of 2y. And 7 times 2 is 14, x times x squared is x cubed. So finally, the answer is 14x cubed, y to the fourth, z cubed, square root of 2y, which is the final answer. Next. Oops. I think this is the end of the discussion about applying laws of radicals when simplifying related expressions. And we'll see you next time.